Welcome, guys. So in this video, I'm just trying to talking about this problem. So I mean, if you go to YouTube, people usually there's many videos proving which pi is irrational. And so by the way, I also have one. Okay, so if you don't know that, you can Google, right? Yeah, but people also ask about what the square root of pi or pi squared. Okay, so that's quickly. Hopefully, we will answer this question in this video. Okay, so I assume that you guys know that pi is irrational. If you don't, then you can go back to see my other videos or go to YouTube to check others' video. Okay, so let's ask about the first one, right? So the first one is trivial, right? What about square root of pi? Okay, so the proof is very easy. Square root of pi is irrational, right? And the reason is that if square root of pi is rational, then the rational number is a field, right? So that means pi is rational. But we know that pi is irrational, right? So which should tell you that square root of pi is irrational. Okay, so this is trivial. Okay, so by the way, Q means the rational number, the field, the set of rational number which forms a field. Okay, but what about What about pi squared? So we know that if pi squared is rational, then pi can be rational or irrational. Because, for example, the square root of 2 is 2, which is rational, right? But square root of 2 can be irrational. So if pi squared is rational, then we don't know pi, right? But if pi squared is irrational, we know that pi is rational. Okay, so we know the following, right? So we know the following is that if pi squared is irrational, then it will imply pi is irrational. Definitely implies square root of pi is irrational. Okay, so actually pi squared is irrational is much powerful than pi is irrational. Okay, so in this video, I will prove. So I will prove the pi squared is irrational. Okay, so let's quickly see the proof. The proof is somewhat lengthy, but I try to keep it easy as possible. Okay, so let's define an, right? N is a let's say positive integer. So and I can assume that pi squared is p divided by q, right? So from this we know that q squared pi squared is pq, right? So q squared pi squared is basically it's an integer. So let's denote z is an integer. So I divide n factorial q to the power n. Q to n divided by n factorial 0 to pi x pi minus x to the power n sine x dx. Okay, so that's my definition for an. Okay, so the first one I want to compute the recursion of an. Okay, so let's do a little bit detail. So the results will be. Oh, let me just write down the results. Okay, so the result will be an will be this way. So you need to do the integration by part twice. Okay, so you need to write down an as this. So yeah, maybe. Okay, so maybe let's finish the proof, and I will come back to prove these things. Okay, so suppose you believe this one. Okay, then you can write down this. You can write down this term, right? This 0 to pi x pi minus n minus x sine x dx. This term you can write down these terms as our what? As our n minus 1 factorial q to the n minus 1 an minus 1. Right, and you can also expand this. So you can get this is equals to qn n factorial to n. So let me just write down. right? And this one we can expand it. So I expanded this pi minus 2x squared as pi squared minus 4x pi minus x. Okay, so the first term will be okay. So there will be two terms. The first term is pi squared term, right? So pi squared term does not give us any trouble, right? Because pi squared term combined is just a constant, right? An minus 2. And also the second term will give you 4q to the n factorial, n minus 1 factorial, divided by q, n minus 1, a n minus 1. So combine, so this x times pi minus term will add this one, so you can get this. Okay, so do a little, by the way, this is n minus 1. So combine all the calculation. We know that an is, let's quickly do it. I'll try to provide all the details, right? So if you think it's to come, you can just speed up, right? By the YouTube. Okay. Right, so it's cancelled, it gives you n, right? So it's cancelled. So right, so you get the so this turns for 2q a minus 1 minus pi squared q squared. So that's because this is q squared, right? And this term will give you n minus 1. By the way, there's another of this term here, so I sorry, I didn't notice. So this term, there will be this term here, so you will cancel this. So get this one, a minus 2 and plus 4q n minus 1 a n minus 1 because sorry about it. There's always this n minus 1 here. Term I didn't notice, so cancel this. Also you get this. Okay, so combine of it, you get an equals to 4n minus 2. So you see, this is my solvent q a n minus 1 minus pi squared q squared a n minus 2. Okay, so we know that the is a0, right? So a0 is 0 to pi sine x dx, which is 2. Okay, and a1 is q0 to pi x pi minus x sine x. So you can use computer or whatever. It's very easy to see this is 4q. Right, so integer, right? So by recursion formula that we know that an is an integer. So basically all the idea is basically prove an is integer. Okay. But then we can see there's a contradiction, right? Because an is defined to be q1 n factorial 0 to pi x pi minus x, right? Sine x to the n dx. So idea is that this is a quadratic function, right? So from 0 to pi, the maximum is x when x equals to pi over 2, right? So actually an is less than. So by the way, this is positive function, right? So an must be greater than 0, and then this an will be bounded by this one. If you use x equals to pi over 2, then this becomes this, right? Times n sine x dx, and now I can bound sine by 1, right? So it's well less than. I just bound sine by 1, so the answer will be qn factorial pi for n pi. Okay, so if n is large enough, then an can be less than 1, right? But greater than 0, so an cannot be integer. So let's prove. So idea is that you try to find this you try to define this integration and prove it. So this is exactly much the same as if somebody want to prove pi is irrational, right? So there's a Leibniz proof which is very close to this, right? Basically it's the same function, and also this. So you can see this that one can just, if you use the integration by part 3 times, then you should be able to prove that pi 3 or pi 4 the rest of this. So basically if you use the same trick, you are able to prove all the pi k is irrational for k belongs to the integer. Definitely is a positive integer, right? It's not irrational, it's irrational for k or a positive integer. Okay, so let's prove. So I think the only missing part is that how can we get this recursion formula. Okay, so let me clear it and provide final details. Okay, so idea is that what we already have is this, right? Okay, so that's we want to do integration by part twice. Okay, so let me just provide idea is that so I just let f so let f of x to be x pi minus x. Okay, so this is just this. Basically, I just want to make a computation easier. So this is the negative cosine, right? So actually, but I don't care, right? So this is f of x, this one, plus n f minus 1 f of prime dx. Right, from 0 to pi, but 0 to pi plugging, right? Plugging will be 0, right? So you get this. You get the same thing, f of prime of x. Also, there's a cosine term here, right? And then we do the same thing here, right? We can make cosine equals to d sine x, and then we do the same thing. So this will be f minus 1 f of prime, so that f is pi x minus x squared, so f prime is pi minus 2x. So pi minus 2x d sine x. Okay, so combine this, we do the integration by part again, so we get this one, right, sine of x, and 0 to pi. Right, if n is larger than greater or equal to 2, then this term is still 0. So we don't care this, and we get the sine of x. Let's do the differential with respect to this. So it's n d dx, f minus 1, pi 2x, f of x. Yeah, ds. 0 to pi. Okay, so combine it, you will get the answer, right? Because there will be n minus 2 sine x. And if you do it again, if you differentiate with respect to this again, then you will get another terms, another f prime of terms. Okay, so this will be the answer. Okay, so idea is that you just do the twice of integration by part, then you go back to my previous page, then you can prove this is. So finally, you will get the same recursion formula that an equals to 4n minus 2 q(an) minus 1 minus pi squared q squared an plus minus 2. But actually, I think in your proving, all you need to know is that a0, a1 is q, and you can sorry, it's integer, and then you try to deduction an is integer. So in your all proof that actually you just need to check the coefficient is positive. You just need to check this coefficient is an integer. So actually, I think you don't need to derive all the exact recursion formula, but you just try to argue that an will be integer. And finally, you try to use bound to bound this an. So the next step will be just bound this an by some number, which is what I just write is this one, pi 2n plus 1 for an n factorial qn, right? And then you can easily say that, oh, if n is large enough, then an will be less than 1 or 0. But this contradiction with an can be an integer. Okay, I think this is the proof strategy. And then the final result will be, so pi squared is irrational, which is definitely implies pi is irrational. Right, so this is pi squared is irrational is much powerful than pi is irrational. Okay, that's it, and I will see you guys in the next videos. Be sure to subscribe to my